Hello everyone. For today's video lecture we're going to talk about power in rigid body systems. So the concept of power is simply the rate at which you can perform work. Because of the work and energy relationship, this is going to be equal to the rate at which energy is changing in our system as well. So putting this into equation, we arrive at the following. Power, P, is going to be the rate of change of work over the rate of change of time, or alternatively, the rate of change of kinetic plus potential energy over the rate of change of time. If we look at the average power exerted over a set period of time, we simply divide the work done or change in energy by the time it took to do that work. So power equals work over delta T. Working in the other direction, we can also define work as the average power times the amount of time spent in our system. So P average times delta T is equal to work. So expanding upon our original relationship, we have some other possibilities in this equation as well. So our average power was work over time. Force times distance is work. So force times distance over time, where distance over time, the change in distance of the change in time would be our velocity. So power could also be defined in a translational system as the force exerted times the velocity we're moving at. This is important for things like the top speed in a car, where the power of the car is going to determine the top speed, where we're mainly overcoming rolling resistance and the drag force on the car. That's our force that we need to balance, and the velocity. And so that drag force plus rolling resistance times the velocity of the car is going to be equal to the maximum power output of our car, and that's how we determine top speed. Alternatively, in rotational systems, we have something similar. So the work over time, where work in a rotational sense is the moment times the change in angle. So delta theta over delta t is going to be our angular velocity. So the moment or the torque in a shaft times the angular velocity of that shaft, in radians per second in this case, is going to be the power that is transmitted by a shaft. And with units and all this, the power units are generally force times unit distance per unit time. So a watt is a unit of power in the metric system. That is a joule per second or a Newton meter per second. Whereas in the US customary system or English system, we've got horsepower is generally what we use. So a foot-pound per second would be the base units. 550 foot-pounds per second is 1 horsepower. So we will see those come up in our problems as well. All right. With power transmission, so this is specific to rotational systems for the most part. So engineers will frequently need to transfer work or power from one location in a system to another. So a common method for doing this is with a combination of shafts, pulleys, gear trains, etc. So we've got a set of pulleys up here. Old-time factories would have a central shaft, and then these pulleys and belt drives running pretty much everything else in the factory. In your modern car, you've got a transmission. So that transmission takes the torque and angular velocity at the input, and it's going to modify that at the output. So we are transmitting power through our transmission in the car, and the drive shaft beyond that as well. And measuring the angular velocity and the torque in a shaft basically lets us easily identify the power being transferred. So torque and angular velocity are fairly easy to measure via sensors. And while belts and pulleys and gear trains and all these things, they modify the torques and angular velocities, one thing that we can discuss here is the concept of power, which will remain constant throughout the entire system. So if we've got a pulley-driven system or a gear-driven system, the torque can be modified, the angular velocity can be modified, the power will not be changed by these systems, at least if we ignore friction. So most of these systems are fairly efficient, and we do have some frictional losses, but ignoring that, assuming like a perfect system, the power will always be conserved in our systems. All right, so finally I want to talk about using power in work and energy problems. So to use the concept of power in work and energy problems, we simply need to multiply the average power times the time to get the work in our problem. So remember, P average times T is going to be equal to work. And so we plug that directly into our equation that we've been using before. So P average times delta T is equal to delta KE plus delta PE. Alternatively, if we wanted to solve directly for power, we just divide both sides by delta t. We'd have this following. So P average is delta KE plus delta PE over delta T. And this is basically the same process that we're using as before. We simply have time as a new piece of the puzzle in here. So if we're talking about power, we're going to have a time element that shows up in our equations. We still want to consider initial and final states, figure out the energies that are present, plug those all in, and solve algebraically for the unknown values. All right, that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.